we are going to build a 3D model of our asteroid orbit. Make this good. You will refer back to it. It really helps to visualize things in 3 dimensions. So we have 2 planes. In my case, I'm just using 2 cards that were given during an event. It's nice. It's card stock. It's kind of big, but little index cards will do as well. You can even go all the way up to legal, just letter size or A4. But it has to have some body to it. Okay, so one of those planes is going to be the orbit of our asteroid, and then the other one is going to be the reference plane. As a reference plane in the OD, we use what's called the ecliptic plane, which is the plane of the orbit of the Earth. So here we'll have the Sun, and we'll have the Earth orbiting the Sun. That's the ecliptic plane, and then this one will be where the asteroid orbits. So let's first work on the asteroid orbit. So to summarize, we are trying to describe the position of our asteroid in space, and that's done via 6 numbers, the orbital elements. There are orbital elements that have to do with the orientation of the plane of the orbit in space, and that's 2 numbers have to do with the orientation of the plane. A third one has to do with within that plane. So once you have those 2 numbers that describe, okay, we're tilted this way, the asteroid orbits in this plane. One of them describes which way the ellipse that's in that plane, which way is that ellipse oriented. That's another orbital element. And then we have 2 orbital elements that simply describe the shape of the asteroid, of the orbit. Is it closer to a circle? Is it really elongated? And also, how big is it? So those are 2 more orbital elements. So we're going to start by drawing just the orbit of the asteroid itself. So we need to draw an ellipse. So this is where we need our supplies. I have a piece of string, and I have pencil, and tape. And also we need something to poke holes, and I need to go get that because I forgot. Alright, so I got it, a little pin to poke holes. So first we need to make a decision on how big and how elongated we want our ellipse to be. So for eccentricity is what describes how elongated it's going to be. We're going to pick 0.35. It makes a nice looking ellipse, and one that fits in ratio like this. And then you'll have to determine how big. Well, how big it is depends upon whether you have something like this or something like this. So what you want to do is to measure how wide on your page you want your ellipse to be, and you don't want it to go all the way to the edge. So roughly have it go maybe from here to here. That's give it some margin and see how long that is, and then multiply it by the eccentricity. So in my case, I can see that if I make my ellipse, I'm using centimeters because this is science, and because I grew up with centimeters and I just like those units better. So for me, 17 centimeters looks like it will make a nice ellipse, a nice width to my ellipse. So if I take this 17 and I multiply by 0.35 the eccentricity, I get 6 centimeters, and that's going to be half of the width of my ellipse. So in other words, I'm going to do 17 times 0.35. I get 6, multiply that by 2, and so that gives me 12. So write that down, or whatever your width is going to be. So I'm going to be working with 12 centimeters. The first thing you need to do now, like now we're drawing, pencil, ruler, locate the center of your page. So mine is 21.5, loosely speaking, 21.6, more convenient. And so 10. You're watching me do mental math in live here. That's gonna be slow. 21, 10 and a half, 10.8. Sounds about right, yeah. A little shy of 12. Doesn't have to be completely exact. Okay, so that's the center here, and then do half the other way. So that's 14. That's easy. That's 7. So 7. Okay, 7 and here. So this does not have to be exact. You just need to have. Oh, maybe if you're smart, you do diagonals, right? Okay. So there's my middle. Okay. From this middle, I'm going to center my 12 centimeters, so 6 centimeters on either side of that. Do that as straight as you can across the page. And so I'm going to have mark here at 12 and mark here at 0. This is at 6. Okay, so these are the 2 points that are really important. So these are foci, focus, singular, so there's one focus and there's another focus. Those are our foci. So I have the center, and then on either side I have the foci. Astronomically, what's going to happen is the sun is going to be at one of those foci, and we're going to put it on the right side. I hope that transferred to the camera, but it's the right side. So the one on this side is going to be the sun. So maybe make it little. There's my sun. It's a star. It's shining. So there's my sun. But we also need the other focus, even though in space there's going to be nothing there. But mathematically it matters that it exists. So the second thing is to use our string. Oh, now I worry that this may not be long enough. Oh no, it should be enough. So your string should be non-stretchy. That's really important because we're going to count on mathematical constructs with ellipses where we count on the distance between. So there's a constant. The way you build an ellipse is any point on the ellipse, if you draw a line between that point and a focus, and then that point and another focus, those two, you add those two distances, and that's a constant. And obviously the distance between the two foci, that's also fixed. So if your string stretches, you don't have a constant distance, you cannot build your ellipse. I figured this out. So you're going to have to figure out how long your string needs to be. You can do that experimentally as well. Maybe that's the route I'll take. I know I figured it out. So if you want to pause the video, do a bit of geometry, and figure out how long your string should be, you can do that. I'm going to do this experimentally. So we need to poke holes. So you're going to poke a hole at each of your foci. Then you want to make those holes not too big, but they do need to be big enough that you can put the string through it. The string, you want to put the string through that. So I think I'm going to pause the video while I struggle with that, and then come back. So I've poked my holes. I used I used the pen to make them bigger, and then I'm threading my thread through it. So I already I threaded it through this first hole, like from front to back. So I just inserted my thread through this hole, and it came out the back. It is coming out the back. And then the fun part is to do the same on the other side. Actually, we want the knot to be on the back side. So you're going to take the other end of your thread, and that other end of your thread needs to go through this hole. I think my holes are big enough that I can do this on camera. Yeah, so there we go. Thread on the other side. So pull those through. It's better to have it too long than too short. But see, I pulled them all the way through, and so now I have this line. So what I want to do, like I said, I'm going to do this experimentally. So I'm going to take this and I'm going to pull it to up here. So this is how high my ellipse is going to go when it comes close to the top edge, and that's good. So this is where I want it. I'm holding it, And I'm going to secure it on the back. So this is where the tape comes in handy. So I'm going to take some tape and I'm going to secure each where the threads are coming through the holes. I'm going to just secure that in place. And I think that's good enough. So let's test that out. So I put tape on the back to where the holes were, so my string is fixed. And then, so don't go crazy when you pull on it, but I can pull on it and it's secure. So that's important. So we are ready to go. I'm going to set this down and I'm going to use my pencil. And I'm going to, it doesn't matter where you start, but I'm going to, so I put my pencil inside my string and I pull on the string. So if you have somebody in your household who's gifted with crafts, maybe give them that job. And then work your way around, just pulling the string taut, but without breaking anything. So I went on this side and then I have to continue on the other side. So like that. So you pull it all the way as tight as it'll go. I lost contact. Whoa. So I'm going to finish this offline. You can see the struggle. So once you have your complete ellipse, come back. All right, so I traced my ellipse. It's very pretty, like this. So what I'm going to do next is go with my pen and trace it, make it neat. And then you can also take off the string. You don't need that anymore. All right, so I've traced my ellipse all clean. At this point, since you're going to be using this as reference, you can write down in the corner our first two orbital elements that we already used to draw this ellipse. So what we used to draw this ellipse, there were two numbers that we used. One was the size of the ellipse. So that's the semi-major axis, and it's A. So it goes from here to here. So when I was first saying, for me 17 centimeters was a good number. My ellipse is 17 centimeter wide. Half of that is the semi-major axis. So my semi-major axis is 8.5 centimeters. Calculator generation. All right. So you can write it down on your sheet. So the semi-major axis is called A. So A, you can say A is the semi-major axis. So that's one thing that we used. And then the other thing that, so that said how wide my ellipse is. And then there's the thing that said how oval it is. So essentially it relates how wide it is to how tall it is, the eccentricity, E. E is the eccentricity. And this I chose because it makes a nice oval that sits on a rectangular page. We chose 0.35 for the eccentricity. So it's good to keep those two, those are our first two orbital elements. So next we need to bring in the Earth. So you have your Sun on this side. So it should be on your right side. So this is at my right focus. And what we're going to do is to, with a pencil, draw a line. And this again doesn't have to be precise, but you want to roughly follow what I do so that you have an orbital model that works nicely and is useful. So you're going to draw a line from the Sun to, we'll draw this line essentially from the Sun to the edge of the page, like that. So you want it to look like this, give or take. The angle doesn't have to be exact, but you want to have a line that goes from the Sun to this end of the page. And then you get to really be crafty. So scissors, and you want to cut along the line that you just drew. So from the edge to right to the sun. Make a slit. So cut that. And then we want to bring in the ecliptic plane. So for the ecliptic plane, you want to take it and insert it. So, say, like this. So insert your ecliptic plane. And you see that this is not very convenient. Here's what we'd like to achieve. We would really like to be able to slide this further. So you know what you've got to do? You need to cut here. You need to cut the ecliptic plane here so that you can slide these two. So leave them like that, lay them flat, and then draw a line again with a pencil, following that line. And so it gives me, you can barely see, but it gives me this line. Don't make it all the way to the edge. That's absolutely not what you want. So stop when you still have a fair bit of paper left on this side. And now you want to cut along that line. So I've cut my ecliptic plane, and now we can insert these two. So you can take them. You can take them, and you can insert them, and now they will go all the way. So you slide them to where they stop. And see, now it's nice because they roughly lay on top of one another. That's kind of what you want to achieve, just so that width-wise they roughly match. They can stick on either side. That's fine. So this is our two planes put together now, the ecliptic and the asteroid plane. So slide it all the way. So now we need to work on. We're gonna set aside our asteroid for now. So this is our asteroid, the orbital plane of the asteroid. You're gonna set that aside. We're gonna work on the ecliptic plane. So the ecliptic plane, and especially the sun, are going to be the basis of a coordinate system that we're going to be using. So we want to label that coordinate system. Oh, I'm going to put these two together again because I did have to mention something else. It's confusing for me. Okay, there we go. So, because here we go. So, and actually, let me demonstrate how this will look for most of the asteroids. So very few asteroids are orbiting in the same within the ecliptic plane. A few probably do, but most of them don't, and quite a few of them are really tilted compared to that. So the asteroid plane really looks more like this in reality. It's going to be tilted. Let's see if I can hold it. So yeah. So it's going to be tilted. So here we go. I think this. So this is my reference plane, and the orbital plane of the asteroid. We have a different view. I'm experimenting with all this, you guys. You can tell. So there's my ecliptic plane, and there's the asteroid orbiting at an angle, as they almost all do. So in the beginning, I was talking about the orbital numbers that describe the orientation of that plane. We'll get to that. But first, I want you to note that we have the sun. Let's find our sun again. So our sun is right here. So the sun is in the orbital plane of the asteroid. It's also in the ecliptic plane. It's what the Earth orbits. So when I remove that, I need to transfer my sun. My sun is here, like right at where we ended the slit. That's where the sun is. So you wanna portray that. So draw a little sun there. Make it a little shiny sun, like that. So now I have my little shiny sun there. The sun is the basis. It's the origin of a coordinate system. One of the one of the coordinate systems we'll use. There's actually a few that we'll have to go through, but one of our coordinate systems has the sun at the center. So now we're going to focus on just the ecliptic plane with the sun in it. And from the sun as an origin, we're going to draw an x and a y axis. So first we're going to draw the x-axis, because the x-axis is set. That's the one that has a set direction in space. And what we choose for the direction for the x-axis is the direction of the vernal equinox. So the x-axis is going to point to the vernal equinox. Where is our vernal equinox going to be? Well, out of convenience, our vernal equinox is going to be, if you hold your page with the sun at the upper corner, you're going to be drawing your x-axis towards the vernal equinox, straight down. Yeah, let's do it straight down. So you're going to draw your x-axis straight down, call it x, to vernal equinox. So it's like this. I just drew a line straight down from the sun, called it my x-axis. It goes to the vernal equinox. So now you need to draw the y-axis. So if you have your x-axis this way, the y-axis, you can see me struggle online. Okay, so hold your x-axis horizontally to the right, draw your y-axis up. Okay, make this look like a normal xy system. All right, so my y-axis, which now that I'm thinking about it, we're not going to be using. We really mostly, well, when we do all the math, it'll be handy to have for some trigonometry, but right now really x-axis determines the direction. So there's my y. It's kind of weird because x is down, y is to the left, because we're looking at this upside down. And then there's a third axis to that. That's the y-axis, and the y-axis comes out this way. It's out of the page. So this is a three-dimensional right-handed coordinate system that we created. So with the orbital plane and the z-axis goes straight up. So that will be, we're done with this plane. So this is the ecliptic plane. Let's label it ecliptic plane. Hold on. Yeah, up here. You want to be careful where you write down things because we're not quite done. We'll label a few more things. So here I labeled it the ecliptic plane. So now you take your orbital plane and put them back together. So look at that, it's nice. I have my suns came together, it's kind of fun. And so there's a line that we want to draw. That's important. So we can see it here because the paper is making a line, but we're going to have to highlight it. And the line I'm talking about is, where's my pencil? Is this line that goes from the sun to, along this slit. So from the sun to where the ellipse is along this slit. So you want to highlight this, and you want to do it on the ecliptic plane. So you want to draw this on the ecliptic plane. Just lay them on top of each other and then trace that. So I don't even know that you need a ruler. You just want to follow the edge of the paper and draw that line. So there. So I did that. I highlighted with my pencil, and then if I take off my asteroid, you have it here. Also, we could have extended our slit alternatively. So that line is important. So you want to go back. I'm going to highlight it just leave pencil. Save the pen for the coordinate system. That's up to you. So I'm going to just make sure with the ruler that this is straight and extend it a little bit. So this line that we just drew, it's called the line of nodes. So I'm going to go ahead and label that. So line of nodes. So there, my line of nodes. Okay, now we are going to introduce one of our orbital elements that determine the orientation of the plane, of the orbital plane in space. And it's an angle, and you draw that angle between the x-axis and the line of nodes. And we denote it by the capital letter, capital omega. So it looks like this. This capital omega is called the longitude of the ascending node. It's one of our orbital elements. So I'm going to go ahead and write it on the ecliptic plane. So this is the longitude of the ascending node. I am writing with a ball pen on a slippery hard surface, so this looks terrible. I don't even know that you'll be able to read it, but that's what you want to write down. Longitude of the ascending node, that's that angle. So it's one of those angles that describe the orientation of the orbital plane in space. And now we're really done with our ecliptic plane. We labeled everything. So we want to come back to our orbital plane. And see, so far we have defined 3 of the orbital elements. The semi-major axis, the eccentricity, and the longitude of the ascending node. So one more that I'm going to write down but that we can't label on here is something called the inclination. So if you put these together and you say my asteroid is orbiting at some angle, the orbit has some, well, I said the word, inclination. It's got some inclination. So this, if I hold this sideways, I'm trying to do this best I can. There's this angle that is between this page and this plane. And that angle is the inclination angle. So this would be an inclination of angle of maybe close to 40 degrees. This would be less, 20 degrees. This would be really high, 50, 60. So we have that angle. That's the inclination angle. So let's just write it down. We can't like label it on the page because it's in space. So call this the inclination. So now we have a third orbital element, the inclination. So that leaves us with 2 orbital elements. So there's one more orbital element that describes the orientation of this of the orbital plane of the orbit. So far, the inclination and the longitude of the ascending node, those 2 numbers, tell us where that plane is. It tells us which orientation in space, which way is it facing. It just tells us how that plane is oriented in space. Now there is one orbital element that deals with the problem of within, so once you set, maybe I'll hold the other side so you cannot see the ellipse. So once this plane is set, we know that the ellipse of the orbit is in this plane, but is it facing this way? Is it this way? Is it this way? Which way is it oriented within that plane? That's what the 5th orbital element does. It's an angle, and it's defined this way. So for that one, what you need to do is to draw another line, and we need to talk about perihelion. So what you want to do is you want to set your ruler exactly going a straight line between the 2 foci. And then you want to draw a line that extends from the sun to the edge of the ellipse. So there's that line. It extends from the sun to the edge of the ellipse. And I drew it along so that it was along that line between the 2 foci. This, you can probably tell, is the point. If the asteroid is here, when the asteroid is here, you can easily tell that right at that point, it is the closest it's ever going to get to the sun. This is the distance of closest approach to the sun. And we call this the perihelion. So another piece of vocabulary. This is the perihelion. It'll be really important for us. So this is the perihelion. And the angle between the line of nodes. So the line of nodes exists on here, but it's in common with this. So this is the line of node. The line of node is where the two planes, I need to do this properly. There we go. The line of node is where the two planes intersect. It's right, you know, those two planes are off of each other. They have different orientations in space, but there's one line when the intersection of two planes, intersection of two lines is a point. The intersection of two planes is a line, and that line we call it the line of nodes. So it exists in this plane. It also exists in this plane. It's in common. So, and we don't need to draw it. It's right along that slit. That's a line of nodes. So that fifth orbital element is the angle between the line of node and the line that goes to perihelion. So that angle is our fifth orbital element. It's lowercase omega. This is not a W. It's a round. It's got a rounded bottom. It's a lowercase omega. And lowercase omega, that angle is called the argument of perihelion. Don't argue. That's the name. So I'm going to label it down here. So argument of perihelion. So there, labeled my little omega is the argument of perihelion. So those five orbital elements that we just drew best we could and defined, they set the inclination of the orbital plane in space. They also set the shape of the ellipse and orientation of the ellipse in space. So with those five orbital elements, we know that the asteroid goes around and around and around right here. It never goes elsewhere. So we have that. Now there's a sixth orbital element, because now that you know what the orbit looks like, you also want to tell us, well, right now, where is the asteroid? Or 2 weeks from now, where is it going to be? So you want to somehow tell people where the asteroid is along this orbit. And that is the only, out of those six orbital elements, that sixth orbital element is the one that's time dependent. The other five are constant, at least over a significant period of time, unless something really extreme happens to your asteroid. It gets nudged and kicked off of its orbit, you know. But if nothing happens to it, it keeps on going and going and going. So those five orbital elements are pretty constant. The fifth one isn't. The sixth one changes with time. And that one, so actually we're going to draw one more angle. Yeah, let's start with this one. So let's say that my asteroid is right here. You can put it wherever you want. If you put it down here, it's going to be more strange. So put it more up here. So draw it somewhere up here. So there's going to be my asteroid. So there's my great looking asteroid up here. And draw a line between the sun and your asteroid. See, I drew that line. Why don't I do that now? Because we'll need that. So this is actually a vector r. It's the position vector. So why don't you just draw it like that? We'll use that. So this is our position vector r. And the angle between the line of perihelion and that vector is the angle that we're going to use to locate the asteroid. So is denoted by the Greek letter nu. It's kind of a U, except it's got a pointy bottom. or a V with a pointy bottom. But that's that angle that one of the angles that we'll use. So that angle nu will grow as the asteroid goes around, and then it's going to go all the way to 360, and then you reset. That is not our sixth orbital element. For reasons, there's some reasons, they're good reasons. We don't use that. We use something else, and that will be introduced later. But it's an angle that is completely related to this angle nu, and we call it M. It's the mean anomaly. So there's the mean anomaly. Someone you really want to befriend. Yeah, there's some really strange names. There's also, at some point, we'll encounter something called the eccentric anomaly. I really like that one. So I don't know if you want to befriend the mean anomaly or the eccentric anomaly. So that concludes our 6 orbital elements. Keep that handy. It'll be really good to have as you go through the material. Bring them to the study sessions, because you can manipulate, you can see how things are. There's going to be a lot of rotations involved, a lot of 3D visualization to do, and if you have a physical thing that you can hold and look at, it will really help. So that was our introduction to orbital elements.